NEC 250.18 specifically addresses lightning rods and the conductors, focusing on the crucial aspect of bonding these systems to the electrical grounding system. Paragraph of NEC 250.18 mandates this bonding. The purpose of this requirement is to create a common ground potential between the lightning protection system and the electrical system. This minimizes the risk of voltage differences that could cause dangerous arcing or side flashes during a lightning strike. When implementing this bonding, the code refers to NEC 250.28b4, which provides specific guidelines on the methods and materials to use for bonding different grounding electrodes together. This section ensures that the connection is robust and capable of handling the high currents associated with lightning strikes. Furthermore, NEC 250.18 directs installers to use a grounding electrode connection in accordance with NEC 250.50. NEC 250.50 covers the requirements for establishing effective grounding electrode systems, including the types of electrodes that are permitted, such as ground rods, ground rings, metal water pipes, and building steel. It also specifies the methods for connecting these electrodes to the grounding system. The proper installation and bonding of lightning rod systems to the electrical grounding system are essential for ensuring the safety of structures and their occupants. By adhering to the requirements outlined in NEC 250.18, 250.28b4, and 250.50, electrical professionals can provide effective protection against the hazards of lightning strikes. It is also important to consult local codes and regulations, as they may have additional requirements or interpretations regarding lightning protection systems. The grounding electrode system should consist of one or more grounding electrodes as described in NEC 250.52. These electrodes can include things like metal underground water pipes, the metal frame of the building if it is effectively grounded, concrete encased electrodes, ground rings, rod and pipe electrodes, and other listed electrodes. The selection of the appropriate grounding electrode or combination of electrodes depends on the specific site conditions and soil resistivity. The connection to the grounding electrode is crucial for providing a low impedance path for fault current to return to the source. This is essential for the proper operation of overcurrent protective devices such as circuit breakers and fuses, which are designed to interrupt the flow of current in the event of a fault. When bonding the lightning protection system to the electrical grounding system, it's important to use listed bonding connectors and hardware that are suitable for direct burial. These connectors are designed to withstand the corrosive effects of soil and moisture. The size of the bonding conductors should be selected based on the size of the lightning protection conductors, as specified in the lightning protection standards. Proper bonding techniques are also important to minimize impedance in the grounding path. This includes using short, direct bonding conductors and avoiding sharp bends or loops. The location of the bonding connection should be carefully considered to minimize the potential for induced voltages or circulating currents. In some cases, it may be necessary to provide multiple bonding connections to achieve an adequate level of protection. Regular inspection and maintenance of the grounding and bonding system are essential to ensure its continued effectiveness. This includes checking for corrosion, loose connections, and damage to the grounding electrodes or conductors. Any deficiencies should be promptly corrected to maintain the integrity of the system. It is important to note that lightning protection systems should be designed and installed by qualified professionals who are experienced in this type of work. These professionals can assess the specific risks and requirements of a given site and design a system that provides adequate protection. They can also ensure that the system is installed in accordance with all applicable codes and standards. In addition to bonding to the electrical grounding system, lightning protection systems may also need to be bonded to other metallic systems such as gas piping, communication cables, and structural steel. This helps to equalize the potential between these systems and minimize the risk of side flashes. The specific requirements for bonding these systems are typically outlined in the lightning protection standards. It is also important to consider the potential for lightning to enter a building through overhead power lines or communication cables. Surge protective devices should be installed at the service entrance and at other critical locations to protect sensitive electronic equipment from damage. These devices are designed to divert surge current to ground, preventing it from entering the building's wiring system. When selecting surge protective devices, it is important to choose devices that are rated for the expected surge current levels and that are compatible with the voltage and current characteristics of the electrical system. The installation of surge protective devices should be performed by a qualified electrician in accordance with the manufacturer's instructions and all applicable codes and standards. In addition to protecting against direct lightning strikes, lightning protection systems can also help to mitigate the effects of indirect strikes, which can induce voltages in nearby wiring and equipment. By providing a low impedance path to ground, the lightning protection system can help to reduce the magnitude of these induced voltages. The effectiveness of a lightning protection system depends on a number of factors, including the design of the system, the quality of the installation, and the maintenance of the system. A well-designed and properly installed system can significantly reduce the risk of damage or injury from lightning strikes. However, it is important to recognize that no lightning protection system can provide absolute protection. There is always some residual risk of damage or injury, even with the best available protection. Therefore, it is important to take other precautions, such as avoiding outdoor activities during thunderstorms and disconnecting sensitive electronic equipment from the power supply. The NEC provides a comprehensive set of requirements for the installation of electrical systems, including grounding and bonding. These requirements are designed to ensure the safety of people and property from electrical hazards. Compliance with the NEC is essential for all electrical installations. The NEC is updated every 3 years to reflect the latest advances in technology and to address emerging safety concerns. It is important for electrical professionals to stay up to date on the latest changes to the NEC. The NEC is published by the National Fire Protection Association, which also provides a wide range of other codes and standards related to fire safety and electrical safety. The grounding electrode conductor is used to connect the system grounded conductor such as the neutral to the grounding electrode. The size of the grounding electrode conductor is based on the size of the ungrounded conductors. The equipment grounding conductor is used to connect the non-current carrying metal parts of equipment to the grounding system. The size of the equipment grounding conductor is based on the size of the overcurrent protective device protecting the circuit. Bonding jumpers are used to connect metal parts together to create an effective ground fault current path. Bonding jumpers are sized according to NEC 250.18. The purpose of bonding is to ensure that all metal parts are at the same electrical potential. This reduces the risk of electric shock. Grounding and bonding are essential for the safe operation of electrical systems. Proper grounding and bonding can help to prevent electric shock, fire, and equipment damage. It is important to consult with a qualified electrical contractor to ensure that your electrical system is properly grounded and bonded. The electrical inspector is responsible for enforcing the requirements of the NEC. The electrical inspector will review the electrical plans and inspect the electrical installation to ensure that it complies with the NEC. If the electrical inspector finds any violations of the NEC, he or she will issue a notice of violation. The electrical contractor must correct the violations before the electrical inspector will approve the electrical installation. The electrical inspector plays an important role in ensuring the safety of electrical systems. The NEC 250.18 goes into detail about grounding electrode requirements, stating that the grounding electrode shall be installed such that it is below permanent moisture level. The electrode shall be free from non-conductive coatings. The electrode shall be installed so that it is protected from physical damage. For rod electrodes, the electrode shall be at least 8 feet in length and shall be driven into the ground to a depth of at least 8 feet. For pipe electrodes, the electrode shall be at least 10 feet in length and shall be buried to a depth of at least 10 feet. For plate electrodes, the electrode shall have a surface area of at least 2 square feet and shall be buried to a depth of at least 2.5 feet. The grounding electrode conductor shall be connected to the grounding electrode by exothermic welding, listed lugs, listed pressure connectors, or listed clamps. The connection shall be accessible. The connection shall be protected from physical damage. The grounding electrode conductor shall be sized according to NEC 250.18. The grounding electrode conductor shall be run in a straight line from the service equipment to the grounding electrode. The grounding electrode conductor shall be securely fastened in place. The grounding electrode conductor shall be protected from physical damage. If the grounding electrode conductor is run through a metal enclosure, the enclosure shall be bonded to the grounding electrode conductor at both ends. If the grounding electrode conductor is run underground, it shall be protected from corrosion. The grounding electrode conductor shall be identified by a tag or label that reads grounding electrode conductor. The grounding electrode conductor shall be inspected and tested periodically to ensure that it is in good condition. If the grounding electrode conductor is damaged or corroded, it shall be replaced. The grounding electrode shall be tested periodically to ensure that it has a low resistance to ground. If the grounding electrode has a high resistance to ground, it shall be replaced. The grounding system shall be inspected and tested periodically to ensure that it is in good condition. If the grounding system is damaged or corroded, it shall be repaired or replaced. The grounding system shall be maintained in good working order. The grounding system shall be kept free from obstructions. The grounding system shall be protected from physical damage. The grounding system shall be identified by a sign or label that reads grounding system. The grounding system shall be accessible. The grounding system shall be inspected and tested periodically to ensure that it is in good condition. The grounding system shall be repaired or replaced if it is damaged or corroded. The grounding system shall be maintained in good working order.